At this point, I will turn it over to Brian, who can start the presentation.
All right, thank you, Howard. And good afternoon, everyone. As Howard mentioned, my name is Brian Barnes. I'm a senior engineer at Atlantic Testing Laboratories. So one of the challenges we face as geotechnical engineers is determining design soil parameters for a heterogeneous material such as soil, which can vary both vertically and horizontally below the surface, and sometimes in a very short distance across the project site. Well, typically, we have to rely on experience and judgment from information gathered during the field investigation, as well as a laboratory testing program on representative soil samples collected at a site. The geotechnical aspects are usually a small portion of the work that goes into the project, but can have a significant cost and time impact on the overall design and construction. One of the things we often deal with is evaluating the risks associated with the different foundation types, such as shallow versus deep foundations, where spending a little more money and time during the design phase can lower the risk and have significant cost savings for the construction of the foundation system. So today's presentation is going to focus on some of the typical geotechnical laboratory tests that are performed on projects in our area. During the design phase of a project, the Geotech Lab can aid in helping the engineer characterize the subsurface conditions for project design. Other construction materials such as steel and concrete are typically produced in the factory setting with quality control performed during the fabrication. However, subsurface soils can vary significantly depending on the mode of deposition by Mother Nature. So to help minimize risks associated with the geotechnical uncertainties, lab testing is performed on representative samples in accordance with established testing procedures, typically published by the American Society for Testing Materials, or AASHTO. And one of the main sources that can occur is sample disturbance during sample collection and testing. So it's important that the proper procedures be followed from sample collection through to the final lab testing. Per the building code in New York State, the laboratory testing program is determined by the registered design professional, which is typically the geotechnical engineer of record for the project. The engineer is a person that knows the specifics of the project. They're usually best suited to determine the number and location samples, the types of lab tests, and the testing conditions to perform the test. It's also important to make sure the laboratory is qualified to run the specified tests. ASTM outlines the testing procedures and how the laboratory should perform its testing. AASHTO has a laboratory accreditation program for running both ASTM as well as AASHTO test methods. And the U.S. Army Corps of Engineers, they have a laboratory validation program to perform testing on their project. So because we can't physically see all the subsurface conditions that exist below a project site, as I mentioned, we rely on a combination of field observations as well as laboratory testing at select locations. Along with the experience in New York State to evaluate parameters for the various geotech aspects of a project. Some of the typical aspects we deal with are shallow and deep foundation systems. And when it comes to the deep foundation systems, there's usually several alternatives that can be chosen for a site. So we're often tasked with evaluating the cost and the time constraints for each of those alternatives. Other aspects, lab and pavements, retaining walls, slope excavation and stability, both during and after construction, and liquefaction analysis. Typically, there's two approaches depending on the complexity and risk associated with the project. The first is to correlate soil parameters to index tests, which typically consist of gradation, sometimes called the particle size analysis, and Atterberg limits, utilized to classify the soil, as well as moisture content and unit weight. These tests are relatively quick to perform, easy to set up, so they usually have a low cost. However, there is a little higher risk using correlation. So we often rely on experience when correlating soil parameters using the index tests. The second approach is to conduct performance tests to measure specific soil properties, such as shear strength, consolidation, hydraulic conductivity. These tests can take some amount of time to set up. They can take a long time to run, so they usually have a little higher cost. However, there's a associated lower risk when designing based on these types of tests. And on some projects, it makes sense to use a combination of both approaches. First, we need to get representative quality samples to the lab. The representative samples should be determined by the engineer based on field observations of the various soil conditions across the site. And the samples are often collected by someone other than the actual lab staff or the engineer. So it's important to have good communication between all parties when collecting samples. Once the samples are collected, it's important to preserve the sample quality so that we minimize disturbance during transportation between the field and the laboratory. We need to make sure we get appropriate sample sizes. And the test methods will usually give guidance on those sizes. So for instance, for a particle size analysis, the minimum sample size for a 3/8 inch gravel is 1 pound, all the way up to 11 pounds for a 3-inch gravel material. So usually at least once a year, we get a client that comes into the lab with a coffee cup, can of gravel, and wants us to do some testing on it. It doesn't cut it. And then lastly, as I mentioned, we want to minimize disturbance from the field to the laboratory. Once they're in the lab, we also want to make sure that they're set up and tested with minimal disturbance. Some of the most common soil sampling methods consist of test pits, which are dug with an excavator, as well as soil borings using a drill rig, where samples are typically collected with a split spoon or what's called a Shelby Tube sampler. And the engineer, they need to determine the appropriate sample methods and the interval for their project. Split spoon samples are considered a disturbed sample because we're driving the sampler into the ground with a 140-pound drop hammer. Whereas the Shelby Tube samples are considered undisturbed because they're pushed slowly into the ground. However, once a sample is removed from its in situ condition, there will be some associated disturbance with the sample. As I mentioned, test pits are typically dug with an excavator, which give a good representation of the soil, shallow depths, as well as groundwater conditions. We're usually limited to about 8 to 12 foot in depth, depending on the size of the excavator. One of the drawbacks to this, it does disturb a rather large area versus a soil boring. So if test pits are dug within a building footprint area, it's important to make sure the test pits are properly backfilled. But based on the test pit, photos here, you can see there's soil layering. You can see the different layers of soil. So it looks like there's some finer grained soils up here, and it gets into a coarser sand as you go with depth. So the engineers are going to determine where to collect the samples, whether or not to take a discrete location or a composite sample. So for instance, if the geotechnical interest is a foundation 4 to 5 feet below grade, the engineer would probably want to grab a sample within this layer. However, the issue is backfill material or fill material for a site. This material is going to be excavated out, and it's going to have to be placed across the site. So it may make more sense in that case to take a representative sample from a stockpile where all those materials get mixed together. So the split spoon sampler, that's the photo here. It's got an outside diameter of 2 inches. It's 2 foot long, and that's the primary sample collection tool that's used in our area with the soil boring rigs. And it's generally used, that can be used for all soil types. One of the limitations, though, is the inside opening is an 1 3/8 diameter. So it's not going to pick up gravel particles any larger than that. The other limitation, we're typically collecting small amounts of sample. So if there is a gravel material, the sample size may not be in accordance with the ASTM test procedure. So once the samples are collected, you can open up the split spoon and then take the sample from the interval specified by the engineer and seal those up and send them into the laboratory. Shelby tubes, they're a thin wall sampler with a sharp cutting edge. They were pushed into the soil using a drill rig or excavation equipment with a jacking system. Shelby tubes, as I mentioned, are considered undisturbed, but once you remove the sample, it's going to be somewhat disturbed. So Shelby tubes actually have a beveled cutting edge on them. But when they're pushed into the soil, it's a little bit smaller diameter than the actual tube, so it reduces the skin friction as the sample goes up into the tube. And these are generally used for soft, cohesive soils. They're not used for gravel, sand, or very stiff, cohesive materials. And once the samples are collected, then the ends are typically waxed and sealed to retain moisture for transport to laboratory. So sample transport procedures are covered in ASTM D4220. We want to make sure we have sealed containers. We need to preserve the moisture content. Color isn't a real engineering property, but some soils oxidize, so you can collect a sample of gray material. If it's left exposed to air too long, it could turn brown. So that can create a problem if we're doing field inspection in the field, and we're trying to compare what we're seeing in the field to what the laboratory is calling out the materials for color. Undisturbed samples, want to make sure those are held upright. Typically, they're held in Shelby tube boxes. That keeps the samples intact as they're shipped to the laboratory. And then lastly, the samples need to be properly labeled, and the appropriate chain of custody documentation should be sent along to the laboratory. I like to show this in my geotechnical presentations just to emphasize the variability of subsurface conditions. It's really by chance that you may or may not find a condition like this. The best we can do is investigate enough locations across the site to get a generalization of subsurface conditions. We just don't want to take one sample at one location for most projects. not sure if this question got thrown out there or not.
Go ahead, Brian.
Okay, thanks, Howard.
Mhm.
All right, so the typical index tests that we run in the geotech lab generally consist of particle size analysis, Atterberg limits, moisture content, and unit weight. And there's the associated ASTMs that go along with those index tests. The main purpose of the particle size analysis is determine the soil types, the percentage of gravel, sand, silt, clay, and the classification of the soil. And depending on if the soil is coarse grained or fine grained, that's going to dictate the methodology that the lab will use to determine shear strength and soil settlement parameters. The soils are mixed. If they have a combination of fine grain and coarse grain, then the engineer needs to determine the methodology based on how they think the soil will behave. Will behave more as a fine grain or more as a coarse grain soil. So the particle size analysis can be used to evaluate liquefaction potential, shear strength parameters, bearing capacity, as well as permeability, which I'll go into more depth for our presentation. Particle size analysis, there's basically two components of this test. The first component is to run the sample through a series of screens down to a number 200 sieve, which has square openings of 75 microns. And that'll determine the percentage of sand and gravel in the sample. So to determine the percentage of silt and clay, we have to perform a hydrometer test where the material passing the 200, that's going to be put into solution. And with a hydrometer, we're measuring the time that it takes for those particles to settle out of solution. So the heavier, larger silt particles will settle out faster than the clay particle. And from that information, we can generate a particle size analysis curve, which tells us a little bit something about the soil. Well, soil type A, this generally indicates a well-graded material. So if you can envision a garbage can, if we were to fill that garbage can with marbles, golf balls, baseballs, softballs, basketballs, you basically have a well-graded mixture. It had minimal voids. They have all the different particle sizes in it. And typically, those materials are going to have a higher unit weight, higher shear strength, and lower permeability around their optimal moisture content. So some examples of this would be a DOT type 2 or a type 4 subbase. Curve B, that's indicative of a uniformly graded material, where if you think about the garbage can example again, it's going to be a garbage can filled with maybe just all basketball sized material. It has a lot of void spaces, and typically they're going to have a lower density and higher permeability due to the higher voids. An example of that material might be like a DOT number 2 stone, which is used for drainage application. A curve C is a gap graded material. There's a gap in it. I don't know, typically that's not something that we see in the particle size analysis that we run. So here's an example of a well-graded material. You can see just based on the shape of the curve, that nice 45-degree angle, nice straight line. And if you look down the percentages, there's about an equal percentage all the way down from the gravels to the clay. And here's what we like to see for a structural fill or a sub-base material. This is generally looks like a well-graded sandy gravel material. You can see the gravel size particles along with the sand size, the smaller particles going in between. From a sand and gravel standpoint, a well-graded sandy gravel. Geotechnically speaking, excessive water is not a friend of soil. As the water content increases or the optimum moisture content, things like the shear strength decrease, the compressibility increases, particularly for fine-grained soils. So the moisture content test, very simple, very common. Basically, the weight of the water divided by the weight of the dry soil. And from a description standpoint, we basically use 4 descriptions. Dry soil is going to be kind of crumbly in your hand, dusty. Whereas moist material has enough moisture to it where if you were to make a ball out of it, it'd be a nice, tight, solid ball. A wet soil, that's going to be on the wet side of its optimum moisture content. And if you were to make a ball of that, the ball might be a little bit spongy, a little bit unstable. And for saturated soils, all of the pores in the soil are filled with water, which would be indicative that sample is taken from below the water table. For sites that may be using on-site materials for mass fills, it's important to know the in-situ moisture content as it relates to its optimum moisture. If the in-situ soils are on the dry side of optimum, the contractor would expect to have to add water to the material to get adequate compaction. If the soils are on the wet side of optimum, then the soils have to be dried out, which would take more time to place the fill, depending on how much above optimum, as well as the time of year the fill is placed. The weather conditions outside right now in the fall, very little soil drying would occur this time of year. We also use the moisture content to identify water-bearing layers. Seasonal perch groundwater is typical in our area, where surface water from rain or snow melt percolates down through the overburden soils and will get trapped on a denser underlaying soil or bedrock layer. Usually when the perch water is encountered in excavations, usually the flow will subside over time until it's recharged by rain or snow melt. For construction dewatering, we can perform particle size analysis in the water-bearing layer. And from that information, an appropriate filter system can be designed for the construction dewatering, which could consist of just simply a geotextile or some sort of granular filter material. The next test, the Atterberg Limits, that determines the liquid limit, plastic limit, and plasticity index for a soil. Whereas the liquid limit, that's defined as the moisture content where the soil changes from a plastic to a liquid state. The plastic limit, that's defined as the moisture content where the soil changes from a semi-solid to a plastic state. And the plasticity index, that's the range of moisture content where the soil is considered in its plastic state. So the photo on the left, that's the apparatus for determining the liquid limit. The soil is put in the grass or the brass cup. There's a grooving tool that makes a groove in it. Then this handle is cranked, which will allow the cup to move up and down on the base plate. So the liquid limit, that's defined as the moisture content where the gap starts to close up at about 25 blows of that cup striking the bottom of the apparatus. The plastic limit over here, that's the moisture content where the sample starts to crumble at about a diameter of 1/8 of an inch. The Atterberg limits, they're used to determine soil classification and to estimate preliminary geotech parameters, typically in conjunction with moisture content or particle size analysis. So some of the things that we can estimate, number one is the degree of consolidation. And if the moisture content, if the natural moisture content of the sample is greater than the liquid limit, the soil is considered under-consolidated. If the moisture content is about equal to the liquid limit, it's considered normally. And if the natural moisture content is less than the liquid limit, it's considered over-consolidated. So if we were to put a new footing over a under-consolidated soil, we would expect to get some settlement and maybe some loss of shear strength because the soil is in a liquid state. On the other side of that, we'd expect less settlement if a foundation was placed on an over-consolidated soil. Compressibility of fine-grained soils. The DOT Geotechnical Design Manual, one of the equations we typically use in that to determine the compression index for settlement of clay soils is the formula I show up there. I like the Geotech Design Manual. It's a pretty good reference manual to have. It gives a lot of information about New York soils, which is good. There's also several correlations with shear strength and shrink swell potential. As far as liquefaction potential, loose non-plastic silts and sands below the groundwater table, they're the most susceptible to liquefaction. So we would typically use the Atterberg limits along with the particle size analysis to evaluate liquefaction potential. These photos just to show what a non-cohesive soil with no plasticity would look like. Over here, a soil around a moist soil, you would expect to crumble in your hand. Non-cohesive side. On the cohesive side, those soils are going to retain their shape. They have moisture to them. And you can typically roll a fine thread like in the plastic limit test for the Atterberg limits. And that brings us to question 2.
Okay, Brian, please continue.
Okay, moving on to unit weight. Unit weight test that's used to evaluate subsurface stresses, bearing capacity, as well as lateral soil loads on structures. And it's applicable to soils that retain their shape. In the lab, we're measuring the weight of the intact sample per the volume of the sample that's being measured. And there's several correlations for compressibility and shear strength using unit weight. Once we have the index test completed, the first step in evaluating soil parameters is to determine the soil type that we're dealing with. The most common classification system for use in engineering applications is the Unified Soil Classification System, which consists of two components. There's a particle size analysis to determine the coarse and fine-grained portions of the sample, as well as the Atterberg Limits to determine the plasticity of the fine-grained material. And here's a typical chart that's utilized to determine the soil classification based on the plasticity index. Well, soils down in this area, they're typically going to be low plasticity salts and clays, whereas soils up in this area are going to be your fat clays. And from a construction material standpoint, the materials down in this area are going to be typically easier to work with in our area, whereas these soils, because they're high moisture content, high plasticity, are oftentimes hard to work with, especially during wet season. And that brings us to question 3.
Okay, Brian, you can continue.
Okay, here's a table from the New York State Building Code that shows presumptive load-bearing values based on various soil types. So you can see over here, based on the US CS classifications of material, sand, silty gravel, clay gravel. The building code has a presumptive load-bearing value of 2,000 pounds per square foot for that material. It's been my experience that the bearing pressures are generally conservative in this table. So doing some additional lab testing can usually increase those values for foundation design. And here's another chart out of the DOT Geotechnical Design Manual that correlates soil type and unit weight to the internal friction angle. This is for cohesionless soils from your non-plastic silts all the way up to a well-graded gravel material. So some of the performance tests we're going to be talking about today are shear strength tests, which are used for slope excavation stability analysis, as well as bearing capacity analysis. The consolidation test for settlement analysis, and the hydraulic conductivity test to determine the flow rate of water through the soil. From the shear strength tests, we're looking to determine the undrained shear strength or cohesion, along with the friction angle of the soil. For coarse grained soils, we typically perform a direct shear test, in accordance with ASTM D3080. There's a few more options for the fine grained soils, which consist of the unconfined compression test, the unconsolidated undrained compression test, and the consolidated undrained compression test. So it's up to the engineer to determine which test to utilize based on how they're going to evaluate the geotechnical issues on the project. And this is a one of the smaller direct shear machines, which is used to determine the drain cohesion and friction angle on a sand material. And typically 3 points are run with this test. Samples are prepared up here in the shear box, which has 2 halves to it. And once the sample is prepared in there, there's a normal force that's put on top of the sample, and then the sample is sheared to determine the shear strength. This test can be performed on either Shelby Tube samples or remolded. So some of the information that the lab needs to get from the engineer are the remolding criteria, the remold in the lab, as well as the normal forces to put on the sample to test. And here's just some example data of 3 points, which shows the normal force and the shear force at failure, so that the failure envelope can be established for that soil. And from that, the cohesion and the friction angle can be determined. The unconfined compression test. This test determines the unconfined compressive strength of the soil. And from that, the undrained shear strength can be determined just using this equation here. So here's a sample. The sample has to be able to hold up its shape. And the sample is compressed without any confinement around it. Where in actuality, if the soil is taken from 10 feet below grade, there's going to be some confining pressure on the sample. Well, basically, the load is put on top of the sample and it's run to failure. Now, these samples, they can be from a Shelby tube or from a remodeled sample in the laboratory. So one of the things the engineer will have to specify for this test is what criteria to remold the sample. The unconsolidated undrained compression test, commonly called the UU test. This is one of the quicker tests for shear strength. But the sample is placed in a flexible rubber membrane, and the outer part of the sample in the cell is filled with water to a specified confining pressure. And then the sample is immediately loaded to failure, which is typically taken as 15% strain or other criteria specified in the test method, without allowing the sample to consolidate. The main purpose of this test is to determine the undrained shear strength for a short-term loading condition, where the loads are placed on the soil and they happen relatively quickly, where the pore pressures that are developed during loading cannot dissipate out of the soil. An example of this would be an embankment. It was constructed quickly over a soft clay. The critical shear strength would occur at the time of construction versus later on, after the pore pressures have been able to dissipate out of the soil. And this test can be performed on a Shelby tube or again remolded. But in any event, the engineer needs to specify the remold criteria as well as the confining pressure to run the test at. And here's a typical Mohr circle plot, again out of the DOT GDM manual. So for the UU tests, sigma 3 is the minor principal stress, which is going to be the chamber pressure. And sigma 1 is the major principal stress, which is the deviator stress at failure, plus the chamber pressure. So from those tests, the Mohr failure envelope can be established and the undrained shear strength can be determined. And you also see on here that the unconfined compression test is plotted, which starts at 0, which that's because the unconfined compression test, there is no, it's unconfined, there's no pressure around the sample when it's tested. The consolidated undrained compression test, commonly called the CU test. It's similar to the UU test in that the sample is placed in flexible membrane. The chamber outside is filled with water. However, under this test, the sample is allowed to consolidate under a confining pressure. And after that consolidation is complete, then the sample is tested to failure. So because of the long time that some clays can take to consolidate, this test can take up to a couple weeks to perform. And this test also determines the undrained shear strength for short-term loading. But one of the things that can be done with this test is we can measure the pore pressures that are developed during the test. And with that information, we can determine the drain shear strength parameters, which can be used to evaluate the long-term conditions. So the DOT Geotech Design Manual, they have a couple tables that are useful. This one here shows the maximum allowable total shear strengths or undrained shear strength. Values of different soil materials. Also depending if they're normally consolidated or over consolidated. And the manual states that these values may not be exceeded without laboratory testing and written permission from the Geotechnical Engineering Bureau. And there's also a table in there with the allowable effective soil shear strengths, which are the undrained parameters. And again, these should not be exceeded without laboratory testing or approval. The one-dimensional consolidation test. Test is primarily used to evaluate the magnitude and rate of settlement of a saturated cohesive soil. And the issue with cohesive soils, it takes time for the water trapped in the void spaces to escape when that soil is placed under a load. So the time is going to depend on the type of clay material as well as the pressure that it's under. But clays are actually charged particles that bind with the water, where sands and gravels are inert. So when a load is applied to a sand and gravel soil, the water trapped in the pores can exit freely, and any settlement would happen immediately for those soils. So typically, evaluating settlement of sand and gravel is usually estimated based on correlations with field data or experience. But for this test, the cohesive soil placed in a 2.5-inch diameter by 3/4-inch high consolidation ring. And the sample is placed in the consolidometer, and it's loaded at several increments where the time and deflection is recorded to develop a consolidation curve. So for this test, samples can be either Shelby Tube samples or remolded in the laboratory. And in any event, the engineer needs to specify the remold criteria, as well as the loading cycle that's different from the ASTM procedure. So then the other thing I want to point out here is the engineer really needs to determine the location for this test. So if there's a 30-foot clay layer that's being evaluated from this test, only about 3/4 of an inch of that is being tested. So the engineer is the one that needs to determine, how many intervals, how many locations to perform. And here's an example consolidation curve. And the data can be plotted in terms of either void ratio or vertical strain. And the things that we're mainly interested with this curve are the maximum pass pressure that's been on the sample, either from having a glacier over the top of the soil when it was being deposited, or maybe erosion occurred, which removed some of the weight of the overburden material over the top of the soil. So from a settlement standpoint, one of the things that we look at is the new loading on the soil is going to be to the left of the pass pressure. We're typically using the recompression index to determine the settlements. Usually the settlements along this range are going to be minimal. However, if the new foundation loads are going to be on this side of the pass pressure, we're going to use the compression index as part of the curve, which once again, as part of the curve, the settlements can be significant. Most geotech textbooks out there will have the formulas and the guidance on evaluating these curves. One of the things, it's sometimes difficult to determine this pass pressure where the curve breaks. Sometimes in the laboratory we don't see that break, which could be, could be something with the soil itself, or it could be from sample disturbance the cause of that. So those are things that the engineer needs to evaluate when you're looking at that data. And that brings us to question 4.
Okay, Brian, go ahead.
Okay, moving on to hydraulic conductivity. There's 2 methods depending on the soil type. For coarse grain soils, the rigid wall is the test that's typically run. And, all soils typically have a high permeability, something like a drainage zone for drainage media. For fine grain soils, the test is a flexible wall, and that's usually performed on low permeability soils, such as for landfill caps, liners, or earth dams. So the rigid wall for coarse grain soils, this is going to be applicable to soils with less than 10% pass in the number 200 sieve. So it's going to be primarily sand and gravel soils. And the sample, because they're granular soils, it's going to have to be recompacted in the mold because we can't take a Shelby tube on those samples. So that's one of the things the engineer will have to specify is what percent compaction to remold the sample. Basically, in this test, is water is allowed to run through the sample, and we're measuring the volume of water versus time to determine the permeability. For the fine grain soils, the flexible wall test, these are applicable to soils with a permeability less than 10 to the minus 4 centimeters per second. I mentioned they're typically performed for landfill projects or earthen dam projects where low permeability soil is required. So the sample will be placed in a flexible membrane, and the outside of the specimen is surrounded by water, and that's going to be put under a confining pressure. And water is actually forced through the sample because if we were to to run the test under gravity, it probably takes several years to determine the permeability. The engineer is going to need to specify if the sample is going to be remolded, as well as the consolidation pressure and the hydraulic gradient to run it. So if you think of a landfill, the pressures and gradients are going to be different for a landfill liner. At the bottom, which is going to be covered with maybe 50, 60 feet of garbage, versus a landfill cap, which is going to be at the surface. And these are typical permeabilities out of the Geotechnical Design Manual. So the permeability of clay is very low, whereas on the high end, the granite have the higher permeability. And that brings us to question 5.
Please continue, Brian.
Okay, and that brings us to the summary here. So just to summarize, I'll need to make sure we have representative quality samples, both from a collection standpoint and getting those to the laboratory. The index tests, they provide a relatively quick and expensive means of correlating engineering parameters such as friction angle, cohesion, carrying capacity, and liquefaction for preliminary geotech information. Performance tests, they determine the specific soil properties, which are typically used for final foundation design. And the RDP, which is typically the geotech engineer record, they determine the laboratory testing program, as well as evaluate all test results. That finishes my presentation. I appreciate everybody for their time.